negative, right?
And therefore VF is
8 to the square root of negative. 17.8185.
if you're stopping there now. That's not a unit thing this time. You said earlier, you just said.
You can't take the square root of a negative.
So if you had thrown the word, the number I in at the end, I would have said, yeah, that's true. But we do have square root of a negative number. Getting rid of the negative sign because it's inconvenient is not the solution. What does our imaginary number tell us? It has physical meaning here. Okay.
Directions in the wrong direction?
No, not a direction thing.
It's not possible,
Why not?
because it's imaginary and you can't go back.
So physically, what does that mean in terms of this problem?
It stops before 20 meters.
Yes. That's what that's what the imaginary answer tells us. It stops before it gets to the end of that. So we need to tweak the problem. So I'm going to tweak the problem a little bit. I'm going to immediately make that 2 meters. Which makes that 18,000. And suddenly this all changes. I could have asked how long, at what point does it stop, but I wanted to have it move at the end for some bizarre reason. So we end up with 1,000 or 10,125 is equal to 500 V squared, V final squared. Say it again.
4.5.
Meters per second. I think one of the master set problems from chapter 7 is a problem similar to this. It does not stop at the end. You don't get the imaginary answer.
Is that a 1? Okay, yeah.
Wait, this?
Yeah.
I thought 4.1, is that what you said?
5.
4.5. You know, 5, 1, it's like a misspelling, right?
Close enough. Sure. Close enough.
4.5 meters per second. Apparently, somebody here can't hear. That is the final speed. If I ask what's the final velocity, then from context, you know it's still going to the right, so it's be positive. 4.5 meters per second. That's the final velocity. In both these cases, you start out with a certain quantity of first momentum and then energy. You lose some, and you end up with a different amount, and then from that we can find speed or velocity. Questions to hear? Then let's collide some stuff. We've already done one collision. We did it where they hit and they stuck together. And that's what I want. So I got a 4 kilogram object. Cruising that way. I'm picking ones where they get
nice convenient integer answers in the end.
Going 6 meters per second. Heading towards one that's 10 kilograms heading to the left.
I believe at 1.
1 meter per second. This is a one-dimensional problem. All right, so we're going to solve basically three types of problems here. So the first one, we're going to have them collide and stick. Very similar to the problem that we did early on. Therefore, what do? Follow the steps from the previous one, example we did.
We're still solving for the momentum of the two stuck objects at that point, correct?
Yes.
Okay, so then the formula would, end up being the initial momentum of 4 kilogram block plus the initial momentum of the 10 kilogram block is equal to the momentum of the 14 kilogram box combination.
So P initial equals P final. The capital P, lowercase p that I've done in the past, sometimes it's really hard to tell, did you draw a capital P or a lowercase p, and sometimes I just get sloppy. Traditionally, the capital P is what you use for a system, and then the lowercase p is for an individual. Like a lot of rules similar to that, it works 95% plus of the time. There are some gray areas. I'm going to try to maintain that convention, but then again, sometimes it's hard to tell lowercase from uppercase. It'd been nice if they picked a different letter. All right, so we have our momentum initial equals momentum final. I have two objects initially. I have just one finally. Because since they stick together, we may as well treat it like one object. Perhaps I should write this on the board. What's the formula for momentum?
P equals MV.
All right. Oh, when Ian talked about the initial momentum equals final momentum, how can we justify that the momentum is conserved?
Closed system.
Yes. There were no other objects involved. Just those two. All right. So, what is the initial momentum of the 4 kilogram mass?
kilograms. Meters per second.
Yep. I'm going to write down Descartes because I'm lazy,
Oh,
but
okay.
kilogram meters per second is absolutely right. Plus, what's the initial momentum of the 10 kilogram mass? Say it again. Descartes? Descartes. Cartesian coordinate system, the whole XY thing, that comes from him. All right, 10 Descartes. No. I understand how you got that, and you were really close, but you did forget something.
Negative.
Yes, that's crucial. The difference is between these two coming towards each other and colliding, and then, or one chasing the other one. And you get very different answers for the chase. Negative 10 Descartes. Doing the fancy math, what is the total momentum after the collision?
About 14.
So we have
Descartes.
is equal to mass of the 14 times the velocity of the 14 final. And so V final is, well, that's easy math. 1. So in a perfectly inelastic collision, they will collide and then head to the right, as its positive answer, head to the right at 1 meter per second. The 10 kilogram turns around, the 4 kilogram does not. It just slows down. This is known, this is what I call, I should say, a perfectly inelastic collision. And I will explain in a moment, or a couple minutes, about why I changed it to what I call it. All right, while we're here, let's take a look at the energy. There is no change in potential energy. It's all traveling on the same plane or in a line. Plus, there's no planet. It's a closed system, so it's only just these two objects. So I have kinetic energy. Sorry to spoil your wanting to shout that out. So initially, my initial kinetic energy for the 4 is 1/2 times 4 times 6 squared. And my initial kinetic energy for the 10, 1/2 times 10 times 1 squared. And so that's 72 and 5. This should all be capital K's. And dramatic pause. And also, what unit should I tack on to this 77?
Is energy measured in joules?
It is.
Okay.
Or if you wanted to piece it together, it'd be kilograms times meters per second squared. That meters per second, whole thing squared. A joule is a kilogram squared. Kilogram, take 2. A joule is a kilogram times meter squared per second squared. So that's the total kinetic energy before the collision. After the collision, K final is 1/2 times 14 times 1 squared. Notice that over here, when I was doing my initial energy, kinetic energy of the 10 kilogram mass, I did not put a -1 in there, although -1 squared would have given me the same answer. But kinetic energy deals with the speed. It doesn't care about direction. All right, so we have 1/2 times 14 times 1 squared. Ooh, I can do that one in my head. 7 joules. So we started out with 77 joules of energy, we end up with 7 joules. Now for the fancy math, how much kinetic energy did we lose?
Right around 70 joules.
Where did it go?
Just poofed.
Actually, to some extent, you're absolutely right, but there's 2 generic answers for something like this. All right, I got my two hands here. We're gonna simulate this, although the masses are closer than that is.
Did they cancel each other out?
Sound.
Sound was part of it, and
Did they cancel each other out?
no, they not a canceling out.
And energy, I guess, sound.
Well, yeah, and so part of the energy went into the sound.
Heat.
Yes,
Heat.
my hands are slightly warmer. And tingly. So kinetic energy is lost here. In most collisions in real life, kinetic energy is lost. All right, questions on this because I'm going to change the problem slightly. Let's see. All right, so we start out with same startup, same initial setup, except afterwards, the 4 kilogram mass is traveling to the right at 3 meters per second. And the question is, what is the final velocity of just the 10? Again, closed system, I know my energy is, momentum is conserved. I start out with 14 Descartes, that does not change. So P initial equals P final. This is 14 Descartes, or at this point, you can get even lazier and just not write units because we know what they are. This is going to be 4 times 3 plus 10 times its final velocity. Again, we find the total final momentum by just adding up the different individual momentums. So 14 is equal to 12 plus 10 VF. VF equals something spectacular.
-8.
No.
Oh, wait a minute, my bad. 22.
Oh, I see what you did.
1.167.
Say it again?
1.167.
No. I don't know what you did that time.
I don't know either now that I look at it.
What, 167, is that, what, 14 divided by 12?
Oh, yeah. It's slightly neglected something there.
0.2. Thank you, 0.2. Subtract 12 from both sides, and you end up with 2 is equal to 10 times VF. So VF is 0.2 meters per second. So now, let's figure out what the kinetic energy is now. I know what the initial kinetic energy is, that hasn't changed. We still start with 77 joules. K final is 1/2 times 4 times 3 squared plus 1/2 times 10 times 0.2 squared. .2.
Yep.
Okay. We still lost kinetic energy. And if so, when it did the same two classic things, mostly. This is what I call an imperfect collision. gonna do one more scenario like this, then we'll talk about the nomenclature, and then we will get into no kinetic energy loss. Questions up to here? All right, so after the collision, this time, we have our 4 kilogram mass bouncing backwards at 2 meters per second. What is the final velocity of the 10 kilogram object? Well, what's my total momentum after the collision? Okay, what is my total momentum after the collision? Nope. That was specific to the second problem, that was the final velocity. Looking for final momentum. I don't know if you said it and I was talking over that, but okay. Let me change the question. What's my total momentum before the collision?
Day card?
Yes, that hasn't changed. This all is still the same. So what's my total momentum after the collision?
14 take off.
Yes. All right, so I have 14 Descartes before and after, because it's conserved in the collision. And that's going to be equal to my final, so that's 4 times -2 plus 10 times V10 final. So the final momentum, sorry, the final velocity of the 10 kilogram mass is
So, would that be 0.6 then?
no.
Two.
2.2 meters per second. All right. Momentum is conserved in all 3 of these cases. Let's take a look at the kinetic energy. I know my initial kinetic energy is 77 joules because, again, my initial condition has not changed. But afterwards, K final, 1/2 times 4 times 2 squared plus 1/2 times 10 times 2.2 squared. 8 plus 24.2. No, that's not right. But that's not what I wanted to do here.
It's 24.2.
That's not what I wanted. All right, so doesn't show any, still an imperfect collision, just like we had over there. I was trying to go for a different one. I'm gonna make a small change here. Questions before I'm gonna change the final velocity of the 4 kilogram mass. Any questions before I do that, using the miracle of an eraser? So given the fact that the 4 kilogram mass is bouncing back really fast. All right.
So 4.6.
All right, so I got 4.6 meters per second, and then my energy, I have 1/2 times 4 times 8 squared, and then 1/2 times 10 times 4.6 squared. So it's 128 plus this
So 105.8.
105.8. And so we end up with a total energy of 233.8 joules. We have gained energy. Unless there was an explosion or some other object in there causing this change, most textbooks call this impossible.
Creating energy out of nothing.
I have a different name for it. Flubberesque. And sadly, you will not find that word in any physics textbook ever. Matter of fact, it's possible you don't find the word flubberesque anywhere. Textbooks call it impossible. Right. I need some room for the board, so any questions before I start erasing? All right, so let's get into the naming of these things. As you might have noticed, what kind of collision it is depends greatly on the kinetic energy. And I'm going to put up 3 different naming conventions, because that won't be confusing. So if the kinetic energy is lost, so if there's a change in kinetic energy and it is less than 0, so we're losing kinetic energy and they stick together. Naming convention number 1 calls this perfectly inelastic. Naming convention number 2 calls this inelastic. Scenario number 2, the kinetic energy is lost but do not stick together. Under naming convention number 1, this is called inelastic. Under naming convention number 2, this is called elastic. The naming convention number 2 assumes inelastic means they stick together automatically, and elastic means there's some bounce involved. If there's no loss in kinetic energy, under naming convention number 1, this is called elastic. And under naming convention number 2, it is perfectly elastic. You can see why certain of these words can have different meanings depending upon your source. Now, for whatever reason, I cannot remember which textbook uses which convention. And it'd be really bad if the textbooks use different conventions, and if there are various websites that use different conventions, they either use the first one or the second one. And in order to eliminate confusion, I decided to go for the unique ones. So, Fox. When they stick together, I call that perfectly inelastic. When kinetic energy is conserved, I call that perfectly elastic. And so what goes in the middle, what do I call it? Since inelastic is not unique, elastic is not unique. A student a couple years ago suggested imperfect, and I liked it. Imperfect. And then if the change in kinetic energy is greater than 0 without explosives, textbook generally call this impossible. And that's what I call Flubber-esque. If you have not seen The Absent-Minded Professor, I strongly recommend it, especially the Fred McMurray version, which I think is superior to the Harry Anderson version, which is superior to the Flubber version. Now, I will tell you, on your last test, there will be a perfectly inelastic collision problem, and there will be a perfectly elastic collision problem. If nothing else, you know that those two problems are gonna be on there. So perfectly inelastic, we've done, they stick together. Usually, not many problems with that one in the end. Perfectly elastic, we got a couple different ways of solving it. All right, questions before we do the perfectly elastic collision? I'm going to show 3 different techniques for solving it. I am not specifying you do one way or the other. I will talk about which one that I tend to do. But the reason why I don't do just one technique and just teach that one technique is that having over the years done 3, I think I've had only one class that settled upon a technique. Usually each individual decides for himself or herself which technique works best for them and just go with it.